Hello viewers, in today's session we are going to discuss an important inequality with the help of second form of Lagrange's mean value theorem. So here we have to show that 1 plus x is less than e raised to x, which is further less than 1 plus x times e raised to x for all x greater than 0, right? So for all positive x, we have to prove this inequality with the help of a second form of Lagrange's mean value theorem, right? So let us first quickly see the second form of Lagrange's mean value theorem with the help of the usual form of Lagrange's mean value theorem, right? Now see, we know that if we have a function, say y is equal to f of x, and this function is defined in some domain D, and if we take an interval, say a comma b, and if this function f of x is continuous in the closed interval a comma b, and this function has a derivative, or this function is differentiable in the open interval, that is a comma b, then Lagrange's mean value theorem says that there is at least one value c which lies between a and b, such that f prime of c is equal to f of b minus f of a divided by b minus a, right? So this is the usual form of Lagrange's mean value theorem, right? So let us slightly modify this theorem to get the second form of Lagrange's mean value theorem by taking b is equal to a plus h, right? So when we take b is equal to a plus h, then this interval is now given by a and a plus h, right? And these conditions remains the same, that is this function f of x is continuous in the closed interval a comma a plus h, and this function f of x is differentiable in the open interval, that is a comma a plus h, then there must exist at least one value of c, right? So now this c is given by a plus theta times h, where this theta lies between 0 and 1, right? So there must exist at least one value of c such that c is equal to a plus theta h, where theta lies between 0 and 1, and then we have f prime of c. C is given by a plus theta h, and b is now a plus h, so we have f of a plus h minus f of a divided by b minus a. So from here we can see that b minus a is equal to h. So here we have h. So now we can write this expression as f of a plus h minus f of a is equal to h times f prime of a plus theta h, and we can now write f of a plus h is equal to, we can take minus fa to the right hand side, so we have h f prime of a plus theta h plus f of a, right? So this statement is known as Lagrange's mean value theorem of second form, right? So these two forms are same with a slight difference, that is in this case we take b is equal to a plus h, and c is equal to a plus theta h, where theta lies between 0 and 1. So f of a plus h is given by h times f prime of a plus theta h plus f of a. So now we'll use this result to prove this inequality. So now let us first take an appropriate function. So we can now write y is equal to f of x is equal to e raised to x, which is defined in some interval, say 0 comma x, where x is greater than 0. Right. So the first step in proving this inequality is to frame an appropriate function, and here we take the exponential function, and we'll take the interval that is a comma b as 0 comma x, where x is greater than 0. Right. So now we'll use this that is the second form of Lagrange's mean value theorem to prove this inequality with the help of this function. Right. So here we can see that this function f of x, which is equal to e raised to x, it satisfies the conditions of Lagrange's mean value theorem. That is, this function f of x is a continuous function for all values of x greater than 0 in the interval that is 0 comma x, and this function f of x is differentiable. That is, f prime of x, it exists for all values of x in the interval that is 0 comma x. Right. So now see, in the second form of Lagrange's mean value theorem, we have this interval, that is the interval a comma a plus h. So if we compare this interval with this one, that is 0 comma x, then we can see that our a is 0. Right. And here a plus h is equal to x, and when a is 0, we have 0 plus h is equal to x, so we have h is equal to x. Right. So now this function is continuous in this interval, that is the closed interval 0 comma x, and the derivative of f of x exists in the open interval 0 comma x. So there must exist at least one c, that is c is equal to a plus theta h. Right. Now a is 0, so we have 0, and here h is x, so we can now write theta x. So we have c is equal to theta x. Now c, it lies between a and b. So we can now write c is greater than a is 0, and here b is equal to a plus h, and a is 0 and h is x. Right. So we have b is equal to x, and here we write x. So we have now this inequality, that is c is greater than 0 and less than x. So now we have this statement, that is f of a plus h is equal to h times f prime of a plus theta h plus f of a. Now taking a is equal to 0 and h as x, we have here x, and then we have for h we can now write x, and f prime of 0 plus theta x, because h is equal to x, and here we have f of 0 because a is equal to 0. So now we can write f of x, 0 plus x is x, and here we have x times f prime of theta x plus f of 0. Now f of 0 can be obtained from this function. So we have f of 0 is equal to e raised to 0, that is equal to 1. So here we have 1. And now we have this important equation where this theta, it lies between 0 and 1. So now let us differentiate this function f of x with respect to x. So f prime of x is equal to a d by dx of e raised to x, that is simply e raised to x. So now let us come to this equation. So here we have f of x. We can now write for f of x e raised to x, and then we have x times f prime of theta x. So f prime of theta x can be obtained by replacing this x by theta x. So here we have theta x. So we can now write f prime of theta x is equal to e raised to theta x. So here we have e raised to theta x, and then we have plus 1. Now let us take this inequality, that is theta is greater than 0 and less than 1. So now let us multiply throughout this inequality by x, and since x is greater than 0, so the direction of the inequality remains the same. So here we have 0 times x, here we have theta x, here we have 1 times x. So this is 0, then we have theta x, and here we have x, right? Okay, so now let us raise all these quantities to the power of e, because here we wish to find out the expression, that is e raised to theta x. So what we will do, will raise these three quantities to the power of e, so that we have e raised to 0, then we have e raised to theta x, and here we have e raised to x. And since the exponential function, that is e raised to x, is an increasing function, therefore the direction of the inequality are intact, right? So the direction of the inequalities remains the same. So now e raised to 0 is 1, then we have e raised to theta x, here we have e raised to x, right? Okay, now let us again multiply this inequality throughout by x. So here we have x, and then we have x e raised to theta x, and here we have x e raised to x. Now let us add 1 throughout this inequality, because we have now here x e raised to theta x. Here also we have x e raised to theta x. So let us add 1 throughout this inequality. So we have 1 plus x, and here we have 1 plus x e raised to theta x, and here we have 1 plus x e raised to x. Now 1 plus x e raised to theta x is equal to e raised to x. So let us replace this expression by e raised to x. So now we can write 1 plus x less than e raised to x, and here we have 1 plus x e raised to x. And this is our required inequality, and that is 1 plus x is less than e raised to x, less than 1 plus x e raised to x for all x greater than 0.